everybody. My name is Dru Roberts. I'm the team leader for Not Fast Just Furious human-powered vehicles at Lamar University. I'm going to take you guys through our final presentation today. So this is just a high-level overview of what we'll be covering. You can feel free to pause it to give it a look over. So here are team member roles. This is just really how we divvied up the work. In reality, we ended up working as a group on almost everything, but this was how our responsibilities were set out at the beginning. So this really showcases our concept generation and how we went through the process of selecting each decision we made. So the top design matrix shows different configurations, how we were comparing them. Bicycle was just two-wheel, normal bicycle. There's the one front, two back Delta configuration trike, and then there's the two front, one back tadpole trike configuration that our team ended up going with, mainly because of its safety rating. It prevents turnovers quite well. And below that, you can see the frame material design matrix. We're comparing just common materials that are used in bike frames. We compared them using their Young's modulus for rigidity, durability, we used hardness charts, and we're just comparing the overall cost, availability, and manufacturability of these different materials as well. And in the end, common steel, we used 1020 cold rolled, ended up being the winner. And that's what we ended up going with for the frame. So after we got our material and configuration selected, we could start modeling. We did all of our modeling in SolidWorks. We modeled the entire thing from the ground up around my body dimensions. You can see over here, this sort of stick figure right here is my body dimensions. We wanted to make sure that there was an ergonomic fit, and that seemed like the best way to do it. All of our simulations were also ran in SolidWorks, all of our FEA, except for the fairing simulations. We ran those in ANSYS Fluent. We also did some hand calculations for simpler things like turn radius, braking distance, and theoretical top speed. So this is our first FEA simulation. We tested this per the specs set forth by ASME to test our roll protection system. There's 2670 newtons applied 12 degrees off of the y-axis at the top of our roll protection system, and we achieved a safety factor of 1.4 with that. This is another case set forth by ASME. It's 1330 newtons applied to the sides of the RPS, and we achieved a safety factor of 1.3 here. And initially, what was set forth by ASME was a 250-pound static load simulation, just to simulate an occupant in the vehicle. And our initial design was a lot thinner on this main frame, or this main spine running through the frame, rather. And we barely passed the static loading at 250 pounds. So whenever we considered the shock-loaded case to simulate going over a speed bump at 15 miles an hour, the static load became 725 pounds, and we had to increase the diameter of this main spine. But after increasing it, we achieved a safety factor of 3.5, which is more than satisfactory. So getting into the fabrication portion, we pulled all the lengths and angles from the pipe sections for the frame out of the model. And to visualize them, whatever was flat enough, we drew out to scale blueprints on the ground so that we had something to mock our pipe up to while we were working on it. And you can see over here, the top one is the blueprint that we drew out, and the bottom one is the finished product of the spine going through the blueprint. So one of the big learning curves for us was making cuts for the frame. After we relocated all of our steel to a team member's house, we lost access to a miter saw. So all of our cuts were actually done with a Metabo, and final angle adjustments were ground in with an angle grinder. And to ensure our welds were tight, the team made saddle cuts on any perpendicular welds on high diameter pipe. You can see an example of a saddle weld over here off to the right. and it just increases the surface area of the weld and reduces gaps. And as we went on, the process became much easier to do. It was a little rough at first, but we got a lot better as time went on. And you can see in this picture to the right, a final product of our welding. The rear forks we did alter because it was impossible for us to actually manufacture what I had modeled on SolidWorks. It was just something that a problem that we had to handle on the fly, and honestly, I like this design more. I think it's more robust. So our team found an experienced stick welder to weld our frame. None of us had experience with welding, so it was very fortunate that we were able to find someone to help us with that. And after the welds were completed, we used the angle grinder to grind down the welds and make them more flush to the design. So for fairings for our bike, we considered many options. Pre-made fairings ended up being not possible because of the lead times on them, and the overall cost would have more than drained the rest of our budget. We explored fabricating ourselves. We had some high density polyethylene sheeting that we were going to use low temps in an oven for a long period of time to get it malleable so that we could shape it into our fairing design that you see over here to the right. But ultimately we were unable to do it just due to time constraints. We finished out our project a couple days before the symposium without the fairing at all. So here's a little simulation just showing a streamline of air particles over our fairing in 15 mile an hour. You can see that it breaks the wind very well. I think it would have been a great addition to our build, but we can only do what we can do. So for the cost evaluation, our initial goal of high cost efficiency, I think that we really brought that to the forefront of our project. You can see this table to the left was our initial budget estimates for the fall semester, assuming that we bought everything brand new. It was all priced out. And the competition, we can exclude that because it ended up being an E-Fest, so there was no travel costs. So around $3,500 for our initial budget estimates, and we ended up spending $219. So even with the competition costs excluded, we still spent less than 10% of our initial estimates by salvaging older parts and getting some materials just through acquaintances. Performance testing, right here we can see the ASME specifications and the requirements, as well as how we performed in each one of them. And some of the requirements we really just did super well. You could see this brake distance at 25 kilometers an hour. We were a third. Our turn radius was half, and our max speed was 1.5 times. That was about 20 miles an hour. 1.5 times the max speed required. Here's braking. And here's the turn radius video. So we did encounter many issues. We had difficulties fundraising during a pandemic. We ended up not really getting any funding aside from Lamar. We had scheduling conflicts between members. We all had busy schedules. So there were specific days that we were able to work and none others. We had delays on our materials ordered. We lost a month of time to that. And there were some issues with the design. We just were unable to produce the geometry of the rear forks ourselves, so we had to make some changes there. And some of the parts that we salvaged from older builds, they really needed to be altered quite a bit to actually fit our frame. So this project, it really tied the engineering curriculum together. I feel like we used every single class from beginning to end while designing this, and it really gave us a true feeling of being an engineer. We had many difficulties in making this, but we persevered and we came out with our final product that you see here on the right. And it was unfortunate that we were unable to compete in person, but I'm glad we were able to do what we could. And thanks for coming by. I appreciate you taking the time to watch our video. Have a good day.